Hi, welcome back to Moose and Chemistry. Okay, now we've been talking about photons, and those are particles, and then some people used to believe that light was particles, and some people believe that light is a wave of energy. Well, what we know today, or our best understanding of that, is it's kind of like both. So, the Brogue came up with this equation to help to put these two things together. And so what he said was, and you thought Planck was bad, lambda equals h, that's Planck's constant, over m times v. Oh, okay, well, we know that h is Planck's constant. Okay, so we got that, and we remember from our last video that Planck's constant is 6.626 times 10 to the negative 34 joules per second. We know that. Okay, that was easy. We know this lambda here means wavelength. Okay, pretty cool so far, not an issue. And we know that this represents the mass of an electron in kilograms. Mass of electron in kilograms. Okay, and wait a minute. We thought that was frequency, right? Wasn't that frequency with C equals lambda V? Remember this? C equals lambda V. Remember we called that frequency? Guess what? It's not frequency. Not for this equation. It's going to be velocity. Whoa, whoa. Yes, we can do that. Scientists have run out of letters and we can rename anything we want to. So the velocity is going to be 3.0 times 10 to the 8 meters per second. That's our constant because that's the speed of light. All right, so much for it being frequency. Okay. So let's go ahead and we'll go ahead and erase something here. Just get rid of it because that no longer applies to this particular equation. All right. So now our mass of our electron basically is like 9.11 times 10 to the negative 31 kilograms. Well, we've also learned that it's 9.109 times 10 to the negative 31 kilograms. All right. You know what? Not a big deal. Works. Works very well. Okay, so let's try a problem using this. Let's set up a problem here. An electron, okay, of mass, which is 9.11 times 10 to the negative 31 kilograms, moves at nearly the speed of light. Okay, remember that an electron is made up of things called leptons. So it's actually kind of a particle, but it does have a wave nature to it. So it moves nearly at the speed of light. Okay, so using the velocity, .0 times 10 to the 8 meters per second, calculate the wavelength of the electron. Calculate the wavelength of the electron. Okay. Sounds pretty simple. Sounds like something we probably do on a weekend when we're trying to have some fun. So, what do we know? Well, let's kind of figure that out. We know the mass of the electron, which is going to be 9.11 times 10 to the negative 31 kilograms. So we know that. Okay? We know that our velocity, not frequency in this equation, is 3.0 times 10 to the 8 meters per second. Okay, we know Planck's constant. Remember that Planck's constant relates the energy in one quantum or photon of electromagnetic radiation to the frequency of that particular radiation. I know every time I say it, it gets a little bit easier. For some of us, it stays a little bit more confused. But, let's see, that's 6.266 times 10 to the negative 34. That'd be joules times second. And so we're looking for the wavelength, which is lambda. All right, so we take this equation. Lambda equals h over mv. Now, all we have to do is just kind of like plug it in, right, to get the wavelength. So lambda equals 6.26. Whoops. I always make that mistake. Hang on, let me get my eraser here. There we go. Oops, need the eraser one more time. I love making these little mistakes. Kind of adds to the fun of the whole thing. So it's 6.626 times 10 to the negative 34 joules per second. Oh, this is so much fun. I really like this. And I'm being serious, actually. 9.11 times 10 to the negative 31 kilograms. Woo, doggy. It doesn't get any more better than this. Times our velocity, 3.0 times 10 to the 8 meters per second. Well, when you do all the math, you come up with 2.42 times 10 to the negative 12 meters. You know, just for heebie-jeebies, I kind of wonder what that would be in nanometers. And then I can tell you what kind of radiation it is. So let's see here. So I'm going to take 2.42 times 10 to the negative 12 meters times, let's see here. So there's 1.0 times 10 to the 9 nanometers divided by 1 meter. So our meters will cancel out. So let me go and do the math here. I'm just kind of curious. You really don't have to do this, but I'm just kind of trying to figure this out here. 242 exponential negative 12 times 1.0 exponential 9. And we get, let's see here, 2.42 times 10 to the negative 3 nanometers. So that would be 0.00242 nanometers. Well, let's see here. What would that fall into? Wow, this would be kind of like gamma radiation. It being that, well, no, not quite gamma. It would be actually somewhere between, let's see, 0.02. Yeah, it could be. Yeah, it's gamma radiation. So I think this would probably be gamma radiation. That's what it seems like. Well, anyway, you guys, you be snarly, and we'll see you back here at Moosing Chemistry.